In the short time humans have been on Earth, we really have left our mark. Human history has been encapsulated with a Quaternary period. This period is the most recent subdivision in the geological record, spanning over the last 2.6 million years, and is characterised by multiple high amplitude and frequency climatic oscillations. Understanding climatic oscillations provides valuable geographic insights into how Earth systems have varied over the past 2.6 million years. In this video, we will attempt to provide an in-depth analysis of the Younger Dryas stadial, a significant Quaternary sub-Milankovitch event which occurred between 12,800 and 11,700 years before present. The Younger Dryas was characterised by return to cold conditions in the northern hemisphere during the last deglaciation. The causal factors behind this dramatic temperature fluctuation have largely been debated to this day, with new supporting evidence constantly emerging.
One argument for the onset of the Younger Dryas event was the collapse of the Laurentide ice sheet. The theory suggests that due to the northward retreat of the Laurentide ice sheet, there was a freshwater flux into the North Atlantic Ocean from Lake Agassiz, when the glaciers locking in the freshwater melted away, evidenced by the 2010 research paper by Merton et al. And their discovery of the resultant flood pathway. This freshwater supply decreased the salinity of ocean water, lowering the density and thus altering the thermohaline circulation. Hence, ambient surface water could not sink. The Gulf Stream was subsequently unable to transport warm water towards northern Europe, which caused temperatures to drop between 5 and 6 degrees in winter and 2 and 3 degrees in summer, which possibly facilitated the dramatic drop in temperature that we see in the Younger Dryas. This theory is supported by evidence that shows there was a large lake sitting on the boundary of the Laurentide ice sheet around the start of the Younger Dryas event, and by the large spike seen in the Delta 018 records around 13,000 years ago.
In contrast, scientific academic researchers such as Firestone et al. Have posited that the Younger Dryas occurred due to the impact of a bolide 12,900 years ago. The bolide exploded above North America, partially destabilising the Laurentide ice sheet, melting ice into fresh water, flowing into the North Atlantic Ocean, resulting in the weakening of the thermohaline circulation system as the original theory suggests. Many have questioned this theory due to the previous lack of evidence. However, new evidence has emerged indicating the abnormally high atmospheric concentrations of dust, ammonium and platinum in the Greenland ice cores, as well as nanodiamonds, charcoal and increased iridium content in both Lake Quetzal in Mexico and in Western Europe. These particles are proxies for an extraterrestrial impact, and as Israde Alcantara et al. Explains, no other hypotheses to explain their occurrence have been found. In spite of this, Holliday et al. Argued in 2014 that this hypothesis goes against the basic laws of physics and is not in accord with the broader physics of the Younger Dryas event. However, the discovery of the vast Hiawatha crater under the Greenland ice sheet in 2018 adds new supporting evidence to the bolide impact theory, further supported by the alignment of the time of impact with the temporal approximations of when the Younger Dryas event occurred.
Theories of the collapse of the Laurentide ice sheet or the impact of a bolide are most likely due to their supporting evidence. These theories on what caused the dramatic cooling seen in the Younger Dryas period may be dismissed in years to come. Yet at this point, out of the two theories, the flushing of cool water into the thermohaline from Lake Agassiz seems to present stronger evidence when considering the tangible flood path compared to the uncertain timing of the bolide impact.